Hi everyone, I'm Martin Isaacson and I'm CEO and co-founder of PerceptiLabs. PerceptiLabs is a globally operated AI company, and we are helping enterprises to compress their time to value by making machine learning easier and more intuitive to work with. And at the core of PerceptiLabs is a unique low-code, no-code visual modeling tool that allows data scientists, our users, to quickly build out and interpret models using an intuitive GUI. And the modeling tool is at the core of the PerceptiLabs platform, which enables multiple useful features for the users. For example, they can work in teams, iterate and prototype through different model types, and keep track of all of these experiments. Our platform runs on OpenShift, which allows users to focus only on creating models and improving them, and not care about the infrastructure and scalability. Today, I will cover several problems that enterprises encounter while working with AI. I will also explain how PerceptiLabs solve these problems, and actually show you the value that PerceptiLabs brings to the table along with Red Hat and OpenShift. Then I will show a demo where we will build a generative model, or GAN, and show how intuitive and easy it is to use PerceptiLabs. When enterprises begin working with AI and machine learning, the first problem they encounter is the complexity and high costs of setting up a fully functional workflow or pipeline. They see how hard it is for their data scientists and developers to understand the models and the models' predictions. On top of that, it's difficult for teams to keep track of all the experiments, understanding who is responsible for certain changes in the models over time. When working with machine learning at enterprises, we need to think about the infrastructure. We need to set up an efficient workflow, just as with software development, where we have to set up a DevOps system. We need something similar for machine learning, and we can call it MLOps. There are several parts of this workflow. There is data management, the data layer responsible for preparing data. Then there is model management and building the models, which does exactly that. And then there is the serving management, where we keep track of the models in live production and monitoring them. All of this has to run on a secure infrastructure, which scales well and utilizes the hardware and resources that are available. With Red Hat and OpenShift, users can use different Red Hat partners that cover the 3 different areas of the machine learning workflow. PerceptiLabs is covering the model management for building and training models. And OpenShift takes care of the whole underlying machinery, making sure that users can run on a secure, scalable infrastructure, which is one of the big things to solve here. We see the model management part as the most complex and the least transparent part of the machine learning workflow. We also see it as the central hub that glues the whole workflow together. PerceptiLabs focus exactly on this, on reducing the risk and compressing the time to value so that the users can get to production-ready models faster. To dig into details, we're providing a drag-and-drop GUI to faster prototype and iterate through different model architectures. We have a lot of visualizations, so users can understand how the model works, explain the predictions, and communicate the results to the rest of the team. It is very important when users experiment and try to get optimized models ready for production that they have a platform to keep track of the iterations and the progress in one central hub. The goal of PerceptiLabs platform is to create an environment for data scientists where they can focus solely on the core important work, on building models. We take care of everything around it. We remove the need to worry about code and bugs, and we provide them with great debugging tools and visualizations for every single underlying variable, so they can improve their models and outcomes. And we empower them to communicate with each other and share the results and collaborate. Let's look at how data scientists build their models today. There are actually a very few choices. One is to build models with code or frameworks such as TensorFlow, Keras, and PyTorch, or by using AutoML. Both approaches have their pros and cons. Just working in code gives you a lot of flexibility, but it's much more complex and it takes a lot more time. Users have to create boilerplate code for visualizations, and they need to make sure that everything is running on the same versions of the frameworks. AutoML has its restrictions. It's basically a black box. It's not easy to understand how the model got to its result, and it only works for a few machine learning techniques. For example, if you want to use reinforcement learning, there are not many AutoML algorithms that could support that. And then there's the PerceptiLabs platform. It's a layer on top of the code APIs and frameworks, just making them more efficient, streamlined, and easier to work with. PerceptiLabs keeps the flexibility of code APIs, as well as gives a degree of automation to the user, while making the process of building models transparent and intuitive. PerceptiLabs enables fast modeling with our visual modeling tool. It's a low-code, no-code, drag-and-drop tool that allows users to build out different models. Users get instant feedback of the output in each component, which is great for debugging. It's an automatic input-output shape-fitting, which means that users can move faster in prototyping and build out optimized models. With some more advanced visualizations, users can visualize every single underlying variable that's being run in the machine learning model. We really take a high-level abstraction of what's really complex here. But users can choose to go into low-level code and reprogram what's going on behind the scenes. In other words, we keep the real flexibility and transparency here. We keep it flexible by making it possible to work in code and with our visual modeling tool, all in the same platform. Users can run on their custom environment. We provide a few dependencies like TensorFlow, but it's very easy to decide which frameworks to run on, so it's customizable. And by having it data flow driven, we keep the same flexibility as if users are working with code. We also empower our users to build models in notebooks if they prefer that instead of or in addition to our visual modeling tool. And to keep it flexible, we have also made sure that they can toggle between the GUI that we have in the visual modeling tool and notebooks, since it's a very popular way of working with machine learning models today. I already mentioned this several times, but I want to highlight it again because it's very important. It is essential to have one central hub for everything, so users can have an overview of all the experiments going on, who is responsible for what changes, and that you can reproduce different experiments that's been done earlier. For example, if someone has built a model and then 6 months later another user tries to figure out who did changes and who is responsible for maintaining the model, in other words, tagging the model to someone, it is tricky if there's no opportunity to gather everything in one structured and organized place. Having a central hub also allows to have an admin who approves if something should go out for production or not. A central hub is a great way to foster collaboration and productivity. Now it's time for a demo. Robert Lundberg, CTO and co-founder of PerceptiLabs, will build a generative model using PerceptiLabs visual modeling tool.
Hi, my name is Robert, and this is a demo for the PerceptiLabs modeling tool. When you first enter the tool, you'll be presented by a project screen where you can view all your different projects. I currently only have one project, so let's jump straight into that one. When you enter a project, you can see all your different models which exist inside that project. You can see their different statuses, if and where they were exported or saved to, how long time it took to train each model, who actually worked on the model, as well as when it was last updated. For this demo, I'm going to create a GAN, a generative adversarial network. To create this GAN, the first thing I need to do is to create a new model. When creating a new model, you have a selection of a few different templates. But for the purpose of this one, we're just going to use an empty template. As soon as you create a new model, you get thrown into the modeling workspace. Here is where you will create your model using the PerceptiLabs drag and drop tool. You do it by dragging and dropping in different components and combining them together with arrows in a data flow driven manner. The different components you can find up here to the left. They're sorted in different categories, where we have the data components, the pre-processing components, the deep learning components, the mathematics components, and the training components. I'll talk a little bit more about the training components later on, but these are the ones which let you build a high variety of different models using a very simple architecture structure. We also have classic machine learning components as well as a custom component. The custom component is essentially a blank component in case you want to custom create it on your own. To start building the GAN, I'm going to drag out a random noise generator. This will act as an input to the generator part of the GAN and will later on generate images which looks like the real images. I'll change so it outputs 100 random values, and we can leave the mean and standard deviation as they are right now. As soon as you apply a component, you'll see a preview of the output of it. You can also see a dimension popping up right above the component, and this will help you as you're building out your model to keep track of how the network architecture looks like. For the generated part of the model, I'm going to create a very simple two-layer fully connected network. I'll put the first one to 128 neurons. And the second one to 784, which will be the same shape as the real images. Also, while we're in this component, I can highlight that each of these components are just a template which generates code in the background. The code which is being generated is what is actually being ran when you're executing the model. To see this code, you can press this Code tab and you'll get full transparency of exactly what is being executed in your components. You can also fully custom edit this component if you want to create something where the settings are not enough. Finally, I'll add a reshape component to reshape this 784 output into an image to make it a little bit nicer to look at. Now that the generated part is done, I'll add some real data for it to train against. The real data I'm going to add in is a dataset called MNIST. It's handwritten digits between 0 and 9, and it's a very common dataset to test your models against. To add this data, I'll drag out a data component and select the file which I want to load. As we can see, the MNIST data is not actually an image right now. This is because the image has been flattened and we need to reshape it back into its original form. To do that, just like before, I'll add another reshape component. and apply it. And then we can see how the real image would look like. Now I'm going to add a switch component. This component allows the model to switch between two different inputs. In this case, it's going to switch between the generated image and the real image. It does this to be able to learn, or try to learn, which image is false or generated and which image is real. The only setting in the switch layer is which components you would start with, and in our case we'll start with the generated image. Now that that's done, we're going to build a discriminator. This discriminator is the one which will try to say if it's a real image or a false one. And the entire purpose of this GAN is the generator part of the model is going to try to compete against the discriminated part of the model to see if it can generate images which are more realistic than the discriminator can say which is which. For the discriminated part, it's going to be even simpler than the generated part. We'll have a fully connected component with 128 neurons, just like before. And then a very simple fully connected component with just one neuron and no activation function. The reason for this is that all this one is going to do is say zeros in case it's a false, if it's not a real image, and ones if it is a real image. Now the model is almost ready. The last thing we need is a training component. So I'm going to drag out a GAN training component and connect it to the end of the discriminator. Except for just running the training loop, this training component also provides almost all the visualizations which we're going to see in the statistic view when we start running the model. In the training component, you have to select which component is the switch and also where the real data comes from. I'm also going to change the batch size from 3 to 100 to make the model a little bit more efficient. Now that the model is finished, we can start training it. To start training your model, all you need to do is press the Run button and then Start. As soon as you do this, you get thrown into a statistic view. This statistic view will give you an overview of how the training goes during the entire training process. In the top part, you'll be able to see an overview of the network as a whole. What we're currently looking at is the real image compared to a generated output. If you remember how the generated image looked before, it was just random noise, while it now already has started learning something. You can see how it's trying to create something which looks like an image. Except for this, we can also see the generator loss, as well as the discriminator loss. And these are measures of how well or poorly this part of the model is doing. The higher the loss, the worse it's doing. How it works though is that the generator loss is going to go up if the discriminator loss goes down. This is because the generator and the discriminator are constantly combating each other to see which one can generate the best image versus which one can see if the image is real or not. So the generator is trying to generate images to trick the discriminator, while the discriminator is trying to get as good as possible on telling if the image is real or not. Finally, in the overview, we have the data distribution, where you can see the distribution of the real data in the red pixels, or red dots, and the distribution of the generated image as the blue dots. Ultimately, you would want the red and blue distribution to end up very similar to each other. Finally, in the bottom right, we have something which we call the view box. The view box is a way to peek into each of the different components inside of the model. To peek into different components, you can press on the map over to the left. Doing this will let you see things such as the outputs of the component, the gradients of the components, as well as the weights and biases of the components. All of this is updated in real time, and its purpose is for you to very easily be able to look through your model and debug what's actually going on. As this one is going to take a while, I'm going to leave the demo here, and I hope it gave a good overview of what you can do in the PerceptiLabs modeling tool. If you want to try it out yourself, you can go to our website, PerceptiLabs.com, and there is a very easy install through pip, so you can install it on your local machine and try it out. We're constantly updating the tool, so any feedback you have is greatly appreciated. And that's everything from me. Thanks.
At the end, I want to say that with PerceptiLabs, our users, the data scientists, can reach their solution faster, work together, and understand how their models are learning and predicting. This in turn leads to saving money and time for enterprises while working with AI. And thank you for listening. Please find more information on our website, PerceptiLabs.com. Thank you very much.